Alright, welcome back to this video lectures in ABE153, and in this video we'll be doing our first sample problem for the fatigue loadings. And this problem is taken from the textbook by Shigley's Mechanical Engineering Design, and this is example 6-2. So the problem gives us, or the problem says that given 1050 HR steel, and this is the specification or designation of steel 1050, and this is hot rolled, so HR, that stands for hot rolled. So given this, we are to estimate the rotating beam endurance limit at 10 to the 6 cycles, and letter B, also estimate the endurance strength of a polished rotating beam specimen corresponding to 10 to the 4th cycles to failure. And letter C, we are to estimate the expected life if a polished rotating beam specimen under a completely reversed stress of 55 ksi. So you might notice that it says polished rotating beam specimen, and also right here polished rotating beam specimen. So that simply means that the specimen that we are, or the material that we are going to solve is actually based on the standard dimensions, standard conditions of a test specimen, right? Because later on we will compute some deviations of, let's say there's going to be changes in the size or changes in the surface finish. Then we have, there are factors to be included in the computations to account for those deviations. All right, so let's solve now. Now for the solution, so let's solving for A. Actually solving or obtain, we need to obtain first the ultimate tensile strength, SUT, and solve for the endurance limit, SE. Right. So once we have this SUT, then we can solve for the endurance limit. And for the SUT, for the ultimate tensile strength, this is actually taken from tables, right? So from the table, this SUT is equal to 90 ksi, right? So that's from the textbooks. If you check this 1050 HR steel, then what we'll find is an SUT of 90 ksi. Right, so this is steel, and therefore the endurance limit is just simply 0.5 of the ultimate tensile strength, and this is just 45 ksi. Right, so this is given in our, I have already discussed this. This is the estimate for steels for some values of ultimate tensile strength of 1,400 megapascals. So if you convert that limiting value, then it's gonna be we are going to use these equations, right? So 0.5 times 90, so this is 45 ksi. Okay, so next is to this one is already solved, right? Because this is the endurance limit. Now for letter B, the endurance strength of a polished rotating beam specimen corresponding to 10 to the 4th cycle. Right, so solving for Sn corresponding to 10 to the 4th cycle, cycles to failure. Right, so our equation is if you recall, this is Sn a to the n, a times n to the b, is simply because if this is the graph, right, so this is 10 to the 10 to the 3, and this one is 10 to the 6. And right here, our equation is this one. Sn is equal to A times n to the B, right? Because right here, for the low cycle fatigue, this is SUT times n to the B, right? So here's our working equation. So first we are going to solve for A and B, because this n is already given. This is 10 to the 4. So if we know A and B, then we can solve for the fatigue strength, right? So let's solve for A first. So A is given by this equation S, F times SUT, the ultimate tensile strength, and divided by the endurance limit, right? So F, what is the value of F? So for F, the value of F is, if we check the graph, what we see here is, right, this is SUT, and this is the value of F, the fatigue friction, what's the term there, fatigue fraction, right? So right here we have a 90 KSI, right? So 90 KSI, so you have to project that here, and then what you get is an F value of this is 0.86, and therefore F is 0.86 times the SUT. The SUT is 90 KSI, and this is squared divided by the value of the endurance limit of 45 KSI. Okay, so if you do the math right here, what you get is 133.1 KSI. Okay, so we now have the A, and we need to solve for B. Right, so for B, the equation for B is negative 1/3 log of F times the ultimate tensile strength divided by the endurance limit. Right, so if we substitute all the values right here, this is 0.86, and this is 90 KSI, and this is 45 KSI, right? And right here is negative 0.0785, right? So just take note, this is negative. So therefore, the value of the strength is this is AN to the B, and our A is 133.1 KSI times the N. So the N is 10 to the 4th, right? 10 to the 4th raised to negative 0.0785. That's the value of B, and what we get here is 64.6 KSI. Okay, so that's it. And for letter C, we are to compute the expected life if a polished rotating beam specimen under a completely reversed stress of 55 KSI. So this is like if for letter B, we are to estimate, or let me draw it here. So it's like this. If for letter B, we are given this value, this N value, and we are to estimate the strength, for letter C, right, so for letter C, it's like this. Given this strength or this stress value, what's gonna be the number of cycles, right? So it's just the other way around. Okay, so let's write it here. So now for number 3, solving now, letter, solving now, letter C. or the fatigue life, fatigue life at 55 KSI, completely reverse stress. Okay, so our equation again is still the same. This is a times n to the b, but we are going to solve for n, right? So for n, this is just simply Sn all over a raised to 1 over b, right? So let's substitute all the values. This one Sn says here 55 KSI. So this is 55 KSI divided by the value of A. This is 133.1 KSI raised to 1 over negative. This is negative 0.0785, negative 0.0785, and this is 7.75 times 10 to the 4 cycles. Right, so here's our answer, and right here's our answer, and for the Sn, this is our answer. Okay, so so if we review what we did is that this is a this is an ideal specimen. I mean, we are considering or solving ideals. I mean the standard specimen, because it says here polished rotating beam specimen, right? So we are solving this one, and what we first did is to obtain the value of SUT, because once you have the ultimate tensile strength, then you can actually estimate the value of the endurance limit. So once you have the values right here, then you can actually solve for the, or you can estimate the fatigue strength or the number of cycles, right? So for letter B, we are in this region. We are in this high cycle region, actually from this point to this point, and the equation that we'll use is this one: Sn is equal to A times n to the b. Now we are going to solve for A and B because this n is given, right? 10 to the 4th. So we solve for A, but in order to solve for A, you need to find the value of this fraction f, right, from the figure, and we obtain that this 0.86, and we substitute all the values, and we get A is equal to 133.1 KSI. And the next step that we did is to solve for B. So given by this equation, then we solve for the B. So once you have A, B, and N, then we can estimate the fatigue strength. So we solve that 64.60 KSI. And the last letter is to the last problem is to solve for the fatigue life at 55 KSI, right? So we use the same equation because we are in this we use the same equation because we are still in this region, because right here, the value right here, this is actually right here, this is the SUT, right? And this is not perfectly straight. It's it has some slope right here because of this equation. So there must be some slopes right here. All right, so that's it. So now let's continue our discussion, and we'll talk about the deviation of the actual material, or actual dimensions or conditions that we have as compared to the standard specimen. Okay, so if we have let's write it here, the test specimen were polished surface at a specified geometry and dimensions, right? So this standard test specimen, this one is loaded right here, fully reverse loading, and it has a standard dimensions, right? So the question is that if we have a part that's not exactly the same as this standard test specimen, then what's gonna happen to our SE, to our endurance limit, right? If our part is not exactly the same as the standard test specimen, right? So what's going to be the value of this SE? Is it the same as the ones we computed? And the answer is no, because what if we are considering actual loadings or torsion loadings, and what if this is not polished, right? The surface is not polished, or what if this is not round? So there's going to be some deviations, and therefore we are going to introduce or we have to introduce some factors to take into account these deviations, and these factors are called marine factors. Right, so basically these are just a bunch of factors that we input, or that we multiply to our endurance limit, to our theoretical endurance limit, so that we can obtain the corrected or the actual endurance limit, right? So SE is just equal to some bunch of factors. I'll just write it here: CF, CR, CS, CL, CT, right? Times, right? So these are a bunch of factors times the theoretical endurance limit. Right, so let's write it here. These are factors to take into account the deviation, and this one is our theoretical endurance limit, or I think the endurance limit based on standard specimen. And this is our corrected or actually it's not I think it's not also the actual, but rather the estimated value. At least I think the a more correct term is this one, corrected value. All right, so this corrected endurance limit. Okay, so let's discuss these factors. This CF. So we have this CF right here, and this is the surface finish, right? Surface finish factor. And this surface finish factor, if we check here, so we have surface finish, like for example ground or machined or cold drawn or hot rolled or as forged. So right here for the factor A, by the way, the equation is that for the surface finish factor, the equation is or let me write it here, surface finish factor. So CF, this is surface finish factor. And the equation, or the way to compute this, is just simply S. CF is equal to A times the SUT raised to B. All right, so what are these values, A and B? And so the values of A and B are taken from this table. And right here, for example, if we have a surface finish of ground or machined or cold drawn, hot rolled, or as forged, then the value of A in terms of megapascals is this one, let's say 1.58, and for the exponent b, this is negative 0.085, and so on, right? So you just have to go to this table and then um, just apply the values in this equation, and you can obtain that. You can obtain the surface finish factor. Okay, next one is material factor. Okay, so for the material factor, this is actually taken from the textbook by Robert Mott et al. And by the way, for the surface finish factor, it's just simply because the test specimen, or the standard test specimen, is highly polished, or polished surface, and therefore there's going to be difference if our part is machined or having some other surface finish. Right, so for the material factor, this one is taken from the textbook by Robert Mott. And right here, there's data for example, material factor from the following list. Like for example, wrought steel, then the cm, the material factor is just 1.0, because that's the standard specimen, I guess. And if the actual material that we use is cast steel, then we have to take into account this difference in material. So cm is equal to 0.8, and for powdered steel we have this value, and for gray cast iron we have 0.7. For ductile cast iron, this is 0.66. Okay, so you just have to go to the table for this material factor. So the next one is the size factor. So CS is size factor. Okay, so for the size factor, we are going to go to the table, and right here for the SI units. So it says here that what if we have a diameter that's less than 7.62, and by the way, this is in mm, and right here above here is the this is in inches, right? So what if we have a size range less than 7.62 mm, then the size factor is just 1.0. But if our diameter is between 7.62 to 50 mm, then here's our working equation, right? So you just have to go to the table to be able to obtain the values of these factors. And right here, this is if the diameter is between 50 to 250, then here's our working equation, right? So what if we don't have a round section? What if we have a rectangular section? Then there's gonna be we have to take into account, or we have to compute for the equivalent diameter, d sub e, for non-round objects, or let's say for rectangular sections, right? And we have in our lecture handouts, and this is also taken from the textbook by I think by Shigley. So for non-rotating round or hollow cross section, this is the equivalent diameter is just equal to this, and for rectangular cross section we have 0.808 times HP. So this is the base, the height raised to 0.5. Right, so once you have all this, then you just have to go to the table and select the appropriate equations. Right, another one is the load factor. So load type factor. Right, so load type factor, C sub L. Okay, so the loadings based on the standard test specimen is actually a bending. Now what if our loading for our actual situation is in axial, or let's say it's in pure tension. So let's write it here. Let's also include pure bending. So if we have a bending, then the CL is equal to 1.0. But if we have an actual loading, then the CL is equal to 0.85. And for pure torsion, the CL is equal to 0.59. Right? So here's our, we just have to select the values. Okay, what else? We also have temperature factor, C sub T. Right? Temperature factor. So for the temperature factor, if we have a temperature range of 450, less than 450 degrees C, then the C sub T is equal to 1. And if it is some range higher than this one, or I think that, let me just write it here, degrees C. So if we have this range, then our temperature factor is 1 minus 0.0058 T minus 450. Okay, so this is this is included in the equations if we have a conditions that's greater than 450 degrees C. All right, and the last one is actually it's not the last one, because there may be still others, but let's just write it here: stress concentration factor. Right, so for the stress concentration factor, this is based on the fatigue regime. Is it in the low cycle fatigue or high cycle fatigues, or greater than 10 to the 6, right? So if the n is less than 10 to the 3, or if we have 10 to the 3, we have this cycle between 10 to the 3 or 10 to the 6, or greater than 10 to the 6, then we have equations right here. Right, so you can just check the textbook about this, but in order to use this stress concentration factor, then you just have to find the values of the parameters right here. Right, so right here, let's say kf is equal to 1 plus q kt minus 1. Right, so there's a lot of data that you need. Like for example, if you are in this 10 to the 6, then you need this q or notch sensitivity, and you also need to find this one. Right, so I just would like to introduce you to this stress concentration factor, but in our homeworks we may not be dealing with this stress concentration factors, because there's just a lot of data or tables or figures that we need to go to in order to obtain this. Right, but anyway, if you have a complete data, if you have the tables, or if you have the or the access to tables and data, then it's also fine. Or I think you should also include this in the computations. Okay, so there's still many others, other factors, but so far we'll only consider the ones that we discussed right here. Alright, so I guess that's all in this video, and in the next video we'll be doing our next sample problem, including involving this marine factors.